Okay, let's get started connecting the SDI 12 USB adapter. This is the program, it's a terminal program that I recommend. And so let's scan. So we have a COM port 5. Apparently this is not the adapter. I haven't plugged it in yet. So let me go ahead and plug in the adapter. Okay, so I just heard the chime that indicates a USB device has been plugged in. So let's go ahead and rescan it. Alright, so now we have two, and this must be the correct adapter. You can unplug and rescan again and see it disappear. So number 8, and the baud rate is 9600, and the data bit 8, no parity, 1 stop bit, and no handshake. So let's get started. Connect. And first I want to issue a command to identify the USB adapter itself, not the sensors connected to the adapter. So that's this command here, ZI exclamation mark. So I'll just type it up here. So ZI exclamation mark, and let's send it over, and let's make sure we don't have any carriage returns. So let's send it over. Okay, so the adapter has identified itself at the address Z, and it is compatible with 1.3 version of the SDI 12 standard. And here's the manufacturer's the identifier or manufacturer's name. This is me, and this is the adapter's model, SDI. So this is the 1.52 version of the firmware. So that means the adapter is working. So if you start with a fresh SDI 12 sensor, then the sensor may not have any address. It means it has an address of 0. But I have a sensor that I have already used, so I can do this, but nevertheless this process is the same. So you want to send this command question mark and exclamation mark. So the exclamation mark is always the ending of a command. The question mark is asking who is on the bus. And at this point, if you're setting up a new sensor, you want to have only one sensor on the bus. So one sensor to the adapter, and you ask who is on the adapter. So here's the response of 1. So this sensor has already been set an address of 1, so it's already working, and you may see a 0. So how do you change the address? Okay, to change the address, so let's see here, this is 0A1, so that means address 0 change into a 1. So I already have a 1, so I'll change address 1 into a 0, for example, and exclamation mark. So I'll send it out. Okay, so the adapter responded with its new address. And if I ask again who's on the bus with this button, so I don't have to type again, here we go. So the identifier is 0. So this address 0 is on the bus, because this is actually permanent. Once you change it, it's going to stay permanent until you change it again. So let's make a change to address 1 for convenience. I'm just going to push this button that sends out 0A1 to turn address 0 into address 1. So let's do that. And here's a response. Address has been set to 1. So if I ask who's on the bus again, only 1's on the bus. Okay, so this is generic how to identify the sensor by its basically name and model number, just the same as the ZI exclamation mark. This is a 1I exclamation mark. So what that makes is the Z, the lowercase z, is the address of the adapter itself. So any function the adapter has, you go through this address Z. Any function that a sensor has, such as measurements, you go through that sensor's own address. So I'm just going to ask sensor at address 1 to identify itself with a string. So let's do that. Alright, so the identification here is address 1, and the compatible protocol is SDI 12 version 1.3, made by Decagon. This was made before the meters group, which was a merger between Decagon and another company. And this is model 5TM. It's a soil temperature and moisture sensor. And there's also some serial number and such. So that's the identification. This means you have good communication. And what you can do next is you can just probe for measurement. So the way that SDI 12 sensors work is once they have an address, a multitude of them can be connected to the same SDI 12 bus. And if you want to talk to one sensor, you just start with that sensor's address, and all the other sensors will not respond. So this command 1M is asking for a measurement. It's not actually asking for the return of the measurement. It's asking for the measurement to get started, because certain measurements will take time to complete. Other measurements are almost immediate. So this measurement will actually tell the sensor to start the measurement, and the sensor will respond by, well, this is how much time you can expect the sensor to finish the measurement, and with whatever amount of values it will return. So that's the first step. And then once the sensor says, okay, I'm done, and then you can send this command 1D0, which reads the first batch of numbers. If this does not respond with all the numbers, then you have to go with 1D1, 1D2, and so on to get more numbers coming out of the sensor. But this is a relatively simple sensor. It has only two values: the relative, the dielectric constant, basically the relative dielectric constant, and also the temperature. So there's only two numbers. So let's get started by sending the 1M. So 1M. See, there are two lines as a response. So the first line is just handshaking that command. It says 10012. Okay. So it basically says the sensor needs 1 second to complete the measurement, and it also it'll respond with, it measures, it takes two values. Okay. And then immediately this came out. That means the sensor has already completed the measurement before the time 1 second expires. So this means it's called a service request. It means the sensor is okay, it's done. It's done its measurement. It needs a service, which means getting the data out. So once this 1 is here, we'll just do that 1D0, and it responds with two values. So again, the 1 is the address. Here is the sign, plus or minus. And this 1.24 is the relative permittivity of maybe the because I have the sensor really close to my table. It's wood. Otherwise, if I hold it up in the air, this will be close to 1. We'll do that next time. And this is the temperature in Celsius. That's an indoor temperature, 22 degrees C. Pretty comfortable. So I'm holding the sensor up in the air, and I'll expect this number to drop to a 1.0. So let's do another measurement. Okay, measurement's over, and then let's extract data. Okay, so 1.00. And let me grab this sensor. So now temperature should rise, and also the relative permittivity will be higher because I'm actually grabbing it. So let's do another measurement. Measurement's done, and return some data. Okay, so that's relatively high because I'm just grabbing it, and temperature is rising. So this is just the basics of getting one sensor's readout. If you have more sensors, for example, if you have a second sensor at a different address, you just use a different address in front of these commands. And sometimes sensors can make different types of measurements, so that this measurement command has its own variations, such as M. It stands for M0. You can also type 1M0 exclamation mark. That is the same as 1M. And then there's also M1, M2, M3, all the way up to M9. And they're all defined by the sensor's manufacturer, what measurements these correspond to. And then for each measurement, the D0 will return the first batch of data. If there are more data, then D1 through D9 will return more data until there's no data. And we can do that. For example, we just sent out D0 and we only expect two values anyway. So what if I say 1D1? Well, there's no more data than two numbers, so the sensor will just respond to this with a 1, and there's nothing else attached to it. There. So this is a good way to decide, oh, there's no more numbers to be read, because certain sensors, they respond with more, they actually have more than 9 measurements, and this format can only provide up to 9 measurements to indicate to the PC that how many values are supposed to be extracted. But what if there's more than that? Certain manufacturers will just say there's 9, but there's actually more, for example 16 or even more. So you just have to keep doing 1D0, 1D1, 1D2 until the response is just the address with no more numbers. Then you know you have extracted everything. And that's how my script is running, is assuming the worst case scenario, we're encountering those sensors that are not honestly telling us how many values they respond back. So we'll have to keep trying until there's no more number. Right. So what else I want to talk about is the adapter itself. So the adapter itself has a number of things that it can do. For example, first you can identify the adapter. We have done that before. So the adapter identifies itself with its firmware version. And there's also a few other measurements I have here. So what are those for? Well, the ZM and ZM1, actually, if you have an SDI 12 plus analog USB adapter, which has a 4-channel onboard high-resolution analog channels, and the ZM will actually return these analog channels measurements. And ZM1 will return the differential measurements among the channels. It will measure the difference in voltage between channel 0 and channel 1, and the difference in voltage between channel 2 and channel 3. So there are only two values returning, and you're using twice as many channels as you were in a single-ended measurement, but you have higher resolution, especially when two voltages are very close and you want high enough resolution, and you should really use differential mode. And if you don't have that situation, you can use single-ended mode for up to 4 analog voltages. So that is those. And if you're using a regular USB adapter, then there's no such high-resolution analog channels. So what if you try and measure? Well, you can try, and it'll still say, yes, I'm going to return 4 values for 4 channels. And yeah, I'm done with the Z saying I'm done. So if I read the values back, and you can see there's actually nothing there. So negative 0.00001. So there's basically nothing there. And you can also try the ZM1, which is supposed to return 2 values, differential channels, differential readouts between 0, 1, and channel 2, 3. So you can also do D0, and you just found there's nothing, right? And this keeps going up until D7, ZM7. So M1, M2, M0, M1 is for an onboard 4-channel high-resolution input, and is also the same if you have an analog add-on board. So the analog add-on board, if you set the address to 0, then it'll actually be the same as the ones with onboard analog channels. So I'm just stacking one analog add-on board onto my my adapter. So what if I measure again? Well, I don't have anything connected to that to the channels, but let's just measure that and do a response. Okay, so there's some random and small voltages. That's because that's the nature of analog channels. Without the sensor connected to the channel could assume various values that also could depend on if you touch the electrode, it'll probably read slightly differently, right? So this is the case for all analog channels. If you don't have them hooked up, they'll just return with some random values. Okay, so if you have this analog add-on to your regular USB adapter, you can have as many as 4 such add-ons. So if each one provides 4 channels, and each one would require 2 separate measurements for single end, and this is, let's do this, and this is for differential. Almost nothing different among the channels. These are just random noise, right? So if you have 2 commands for each add-on board, you can do up to 4 add-on board, each one having a different address. You can set on the add-on board's jumpers, and then you need 2 times 4, basically 8 commands. So ZMs or ZM7 are all about those. And here's also ZM8 and ZM9. So what are those then? Okay, so I can do a ZM8, and it says, okay, so there are 8 things to be returning. So let's read them. Okay, and only 4 return. So what do? Well, we keep issuing more, right? ZD0, ZD1. Okay, so it basically responded with 8 values now. So now there's no more. You can try ZD2. There will be just a Z as a response. So what these numbers mean, these are also analog channels on the adapter's optional analog digital input ports, and these are lower resolution. As you can see, there are only 3 digits after decimal. These, there are 4 to 5 digits, and also this one depends on the voltage of the USB port, so it's only a nominal value. I wouldn't really trust this more than about 0.5% to 1%, right? And if you have something that's rough, that's not really necessarily precise, you can use these channels if you just solder on a header to that port. And these are the digital inputs corresponding to these values. Apparently, none of these values is high enough to count as a high, so they're all zeros as lows. So that's what the M8 does. It treats the inputs as analog or digital. It reads back both versions as analog and as digital. It depends on what you're hooking them up to, and you can decide what to keep. So there's also one more thing, is the ZM9. So what the 9 does is different. So let's push this button here. So it says it returns 4 values. So what kind of values do we have here? So let's push that. Unfortunately, they're all zeros, but these are different zeros. This is actually a counter, a digital counter. So if you have pulses, such as pulses coming out of a flow meter, or pulses coming out of a ring gauge, the tipping spoon ring gauge, each time the spoon tips, it gives out a pulse. So this is a pulse counter, just basically treating all the 4 inputs as pulse counters, and then count the pulses since last time. So if you do it again, and if there were pulses since you last read the pulses, those pulses will come out. So if you read pulses every minute, you'll have the pulse per minute readout for these. I don't have these proper sensors hooked up, so I don't really have any of these values. But if you want, you can use this as pulse sensors. Right, so let's see. Let's pause. Okay, so we have a diagram here. This is a slightly older diagram, but that's okay. So what I meant was this port here, which is optional. You can either ask me to test the port and solder it on for some additional charges, or you can buy yourself these 0.1 inch spacing 12 pole terminal blocks. You can solder this on yourself. Let me see, there's a diagram here. So this is when you solder it on, it looks like this, and you can have channels. Basically, here's a 0. This doesn't print out too well. 0, 1, 2, and 3. So you have 3 channels that are acting as analog or digital, and you can also use them as pulse counters. So this is basically the conclusion of this demo. How do you use this SDI 12 USB adapter? It's rather easy to use. What I have showed you was just basically kind of a debug. Try to use the this serial monitor to find out what's happening. And I think the next natural step is to run the Python scripts to maybe get a few readings out using a single sensor, maybe add more sensors to it. I have Python scripts that can do multiple sensors and also reading the analog voltages from these add-on boards, and also more sophisticated data logging scripts for logging across multiple SDI 12 USB adapters, so you can deploy more of them depending on your topology. And if say one Raspberry Pi or PC at a central location is not enough to span the distance, you can even use some of these things you can buy from market. You can extend a USB port up to 100 feet. That's quite some distance. It's a type of adapter that uses the RJ45, the category 5 or category 6 cables for Ethernet, and it uses higher voltage signaling to pass USB signals across a greater distance than what a USB cable can do. So if you do that, you can span a wider range of distances, and sometimes you'll be able to do that with a single Raspberry Pi and the multiple SDI 12 adapters at fairly far enough distances, not very far across a field, but far enough to cover a small area. And then you can use the more sophisticated logging script, and all the scripts are free of charge. You can make any modifications you want. You can use it commercially if you want. It's all provided for you for free. So I have other videos to cover those. If you need any details, just contact me. Thank you.